Hello everybody and welcome back to our introductory course on machine learning. This is Unit 2 on supervised learning, Video 2, linear methods for classification. So we're going to dive into more of the details, look at some of the actual math behind classification tasks, and as well as expand upon our simplest case. So let's get started. This is going to be a two-part video, and again, the first one is going to expand our simplest case and talk about learning multiple classes. So what do we do when we have more than just family cars in our example from video 1? The second part is going to talk about linear models. Least squares and nearest neighbors are going to be our methods for solving those linear models, and these are what are actually going to be used to solve these classification problems. These are the linear methods that we are going to talk about. And so let's begin. So this is the simplest case continued, and the family car two-class problem is going to expand. In the general case, we have k classes denoted by C of I, where I is going to go from 1 to our number of classes k. So this is, if we don't just have family cars, we also have sports cars, luxury cars, and things like that. So in machine learning for classification, we would like to learn the boundary separating the instances of one class from instances of all other classes. Thus, we view a k-class classification problem as k two-class problems. So let's take a look at what that means. Here we have our inputs, just like before. However, our R is going to be defined by the individual class that it applies to. And so learning multiple classes is going to look like this. We're going to have many hypotheses now. In fact, we're going to have one hypothesis for each individual class in our problem. So in the k-class problem, we have k hypotheses to learn. And then the total empirical error is going to take a sum over the predictions for all classes over all instances. So here, we're not just looking at one individual hypothesis now, we're looking at many hypotheses over many classes. So here's a easier to understand graphical representation of what I have just said. And again, this is talking about our problem from before. So we have engine power and price as our two-dimensional input space. And here we actually have three classes. We have sports cars, family cars, and then luxury sedans as well. So each individual hypothesis is simply trying to separate one class, such as the family car, from all other classes. So that is why you have a bounding box around just the family car. And the sports car hypothesis is trying to separate the sports car class from all other classes. So this is what we mean when we say we view a k-class classification problem as k two-class problems. So each individual hypothesis is trying to separate the data into like a family car class and not family car class. So it's a two-class problem, or sports car class or not sports car class. And then since we have three different classes in this problem, we're going to have three hypotheses, and we're going to do three two-class problems. So this is more of just a general case. This is again, our simplest case scenario. It's just an example to explain the reasoning behind how we're solving these problems. Let's take a look at the actual math or the actual methods that would be used to solve these. So most often, these are going to be linear models. And linear models are going to take an input such as this, where x is just going to be a column vector of all of our inputs, x1, x2, all the way to xp. So we have p inputs here. And then t is just going to denote a vector or matrix transpose. And again, x being a column vector, so the transpose here is going to be a row vector. And then here is our linear model. So the term b naught here is going to be the intercept, also known as the bias in machine learning. When we talk about setting the parameters for these machine learning networks, we're going to talk about setting the bias, and this is where that value is coming from. This is very similar to y equals mx plus b. Here we're just summing over all of the individual inputs. That's why we have the summation from j equals 1 to p. So we're looking at each individual input, and then our beta hat is going to be the parameters that we are trying to fit this model with. So this is our linear model written in matrix notation. So it's often convenient to include the constant variable 1 in x in our inputs so that we can include beta naught, our bias, in the vector of coefficients beta hat, and then write the linear model in vector form as an inner product. And that is what is going on in this lower step. So again, linear algebra notation, so important if you want to understand machine learning methods, because you're more often than not going to see the matrix notation denoted in the lower equation here. So in the input-output space, the point x, y hat is going to represent a hyperplane that is separating the classes in our problem. Viewed as a function over the p-dimensional input space, f of x equals x of t beta hat, our bottom equation, is linear, and the gradient f prime of x equals beta, where we're taking the derivative with respect to our variable, which is the input x here, is going to be a vector in input space that points in the steepest uphill direction. So again, this is why it's convenient to write it in matrix or vector notation as an inner product, because taking the gradient of this is very simple. We can quickly see that it's just going to be beta, the parameter that we're optimizing, and we can move forward from there. So let's take a look at an example of this and how we'd actually solve this linear model. There's a couple different methods for solving the linear model, being least squares and nearest neighbors. So let's take a look at the first one, least squares. So how do we fit the linear model to a set of training data? There are different methods, but by far the most popular is the method of least squares. In this approach, we pick the coefficients beta to minimize the residual sum of squares. So here's the residual sum of squares. Again, you notice the x of I of t times beta is just going to be our prediction for each individual point, whereas y of I is going to be the actual result. So the residual sum of squares with respect to beta is a quadratic function of the parameters, and hence its minimum always exists, but it may not be unique. The solution is easiest to characterize again in matrix notation. So let's go over that really quickly. If you're not that familiar with linear algebra, we're not going to spend too much time on this, but we want to look at the results of what this gives us. So the residual, or where x here in these equations is an n by p matrix with each row an input vector, and then y is an n vector of the outputs in the training set. So differentiating with respect to beta, we get the normal equations. So these solutions are going to allow us to solve for beta given the outputs of our example problems or whatever problem we're trying to solve. And again, you're more often going to see beta written as this in matrix notation just because it's easier to characterize and easier to solve in matrix notation. But you don't necessarily need to use beta in that form if you're just applying these functions. So let's take a look at an actual example of using least squares to find solutions. So this is going to be our example problem. This is just simulated data. It doesn't mean anything. There is no background behind this data. We'll take a look at the data next. And then we have our function y hat equals x of t beta in matrix notation again. And then we're going to have a linear regression model to fit this data where y is coded as 0 for blue and 1 for orange, and the fitted values of y hat are converted to a fitted class variable g hat according to the rule you see on the right. So we have two classes, orange and blue, and we want to fit them in the output class g as blue or orange. So let's take a look at the data. Here we have a distribution of orange and blue points, and the two predicted classes, orange and blue, are separated by the decision boundary denoted in this graph, which is linear in this case. We see that for these data, there are several misclassifications on both sides of the decision boundary. So we used our least squares method, and we found a linear solution. In this case, our xt, our transpose of x times beta hat, is simply equal to 0.5. So we have a linear function separating our orange from our blue, and so the predicted values you see, the top region of this graph is all orange. That's our predicted G, and the bottom is all blue, where we're predicting G again as to be the class blue. So several misclassifications, many misclassifications actually. This means that perhaps our linear model is too rigid. Perhaps a linear model wouldn't fit this data the best. However, there are several other ways to solve linear models, the next being nearest neighbor. So let's see if that can give us some better results on this same data. So here's nearest neighbor. The nearest neighbor method uses the observations in the training set closest in input space to X to form Y hat. Specifically, the K nearest neighbor fit for Y hat is defined as you see here, where N of K of X, Nk of X, is the neighborhood of X defined by the K closest points in the training sample. Closeness implies a metric, which for the moment we're going to assume is Euclidean distance. So in words, we're going to find the K observations with xi closest to X in input space and average their responses. So here K can range from 1 to any number essentially, and that's going to change our nearest neighbor approach slightly depending on the K that we pick. So we're going to look at two examples where we're picking different values of K to show how that is going to differ. So let's take a look again at our data. Here we're using a 15 nearest approach. We're using the same training data as before and use 15 nearest neighbor averaging of the binary coded responses as the method of fitting. Thus, Y hat is going to be the proportion of oranges in the neighborhood, and so assigning class orange to G hat amounts to a majority vote in the neighborhood. The colored regions indicate all those points in input space classified as blue or orange by such a rule. In this case, found by evaluating the procedure on a fine grid in the input space. We see that the decision boundaries that separate the blue from the orange regions are far more irregular than our least squares approach and respond to local clusters where one class dominates. So this is a much better fit looking at neighborhood averaging, where we're taking into account the 15 nearest points in this specific example, and we get a more irregular boundary that actually separates the two classes from each other much better in our input space. And so the top left here is orange and the bottom right is all classified as blue, so that you see, for example, on the far right side of this graph, we still have several misclassified orange points where the neighborhood, the 15 nearest neighbors are going to be blue, but there's still orange points in our input data. And this likewise in the top left, we have some blue points that are misclassified as well. So let's compare this 15 nearest neighbor approach to a 1 nearest neighbor. Here we're only taking into account the actual closest point. So this shows the result for 1 nearest neighbor classification. Y hat is assigned the value of the closest point in the training data. In this case, the regions of classification can be computed relatively easily. Each point has an associated tile bounding the region for which it is the closest input point. For all points X in the tile, G hat of X is just going to be equal to GI, so it's the closest point. The decision boundary is even more irregular than in our 15 nearest neighbor approach. So in the 1 nearest example, we see that far fewer training observations are misclassified than in the 15 nearest. But this should not give us too much comfort though, since in the 1 nearest example, none of the training data are misclassified. If you look at this graph, you actually see that there are 0 misclassifications. A little thought suggests that for the K nearest neighbor fits, the error in the training data should be approximately an increasing function of K and will always be 0 for K equals 1. However, we talked about generalization in our first video. This fit to this data is probably not going to generalize very well to future data. So when you get an additional input point, it's probably not going to perform as well as it did on the training data. In fact, it definitely won't, because we performed perfectly on the training data. So an independent test set would give us a more satisfactory means for comparing the different methods. and that independent test set just being more additional data points that we're going to see if they're classified correctly or not. And again, in that test set, arguably this 15 nearest neighbor classifier is going to perform much better than this one nearest neighbor, even though we had 100% accuracy in our training data here in the one nearest neighbor classifier. So that is why it's always important to look at an independent test set when you're evaluating these methods, because training data accuracy is not always the best indicator of how well the algorithm is going to perform. So, in summary, a large subset of the most popular techniques in use today are variants of these two simple procedures: least squares or nearest neighbor. In fact, one nearest neighbor, the simplest of all, captures a large percentage of the market for low-dimensional problems. And again, this is just the basics of nearest neighbor. There are several methods that can be used to enhance these methods, such as kernel methods, the use of high-dimensional spaces, local regression, basis expansion, and projection pursuit. So it can be improved upon, but again, it's either least squares or nearest neighbor are going to be your two most popular techniques for solving linear models for classification. And that concludes this video on the linear methods for classification. Video 3 is going to talk about linear methods for regression. So what happens when we're searching for a numerical output instead of just trying to separate the data into several classes. Thanks for listening.